Okay, welcome back to Calculus Conundrums, Applications of the Derivative. Feel free to subscribe here if you like what you see. I'm going to talk about Newton's method here. Newton's method is a technique for approximating the real zeros of a function. You can call this taking a ride on the tangent line. Now, I'm not going to cover the derivation here. This first page just shows you where the formula comes from for Newton's method. So what I'm going to do, and you can pause this and you can slowly read through it. You can read through it, take notes if you want to, but basically this is just deriving this method. And at the very end of this, you'll get a formula for what I call the xn point, and notice that that formula to find the xn point is the n minus 1th point minus f of x evaluated at the n minus 1 point divided by the derivative of x evaluated at the n minus 1 point. Now it's better understood with an example, so let me show you how this works. So we're going to use Newton's method to estimate the zero of this function, x squared minus 7. Now, since we want I want a positive root, so I don't want the negative root of 7. The solution to this would be plus or minus the square root of 7 if we set this equal to 0 and solved it. But I just want the positive root. So we know that if we evaluate this at 2 squared minus 7 is negative 3. And then if we evaluate it at 3 squared minus 7 is 2. So by the intermediate value theorem, there must be some number between 2 and 3 such that f of that number equals 0. Okay? So let's start with the number halfway between 2 and 3, 2.5. Now I'm only going to go through 3 iterations so you can see it work. Okay, we already know the answer is roughly square root of 7, which is 2.64575, because you can easily solve this. Alright, but now what do we need to do this? Well, first of all, we need a starting point. So I'm going to use 2.5 as my starting point. So that's going to be my x1. Okay? And then I need the function, which we know is x squared minus 7. And I need the derivative of that function, which we know is 2x. So now what I'm going to do is I want to find x2, my x2 point. So go back to the formula. Let's remind you of what that formula says. So if I want x2, I take x1 minus the function evaluated x1 divided by the derivative evaluated x1. So I would have 2.5 minus, and then evaluate the function at 2.5. So plug 2.5 in here, and that'll give me 2.5 squared minus 7. And then the derivative evaluate at 2.5. So plug 2.5 in here, and that'll give me 2 times 2.5. And then just use a calculator to get this. And that's going to give me 2.65. And so that's, remember, the answer was really 2.64575, so 2.65 is not too bad, but we can even get it closer. So if we now take 2.65 and call that x2, and then to get x3, we take 2.65 minus the function evaluated at 2.65 divided by the derivative evaluated at 2.65. Then we get this expression, and we get 2.6457. So that's even better. And then if we did it one more time, x4 would be 2.6457 minus the function evaluated at 2.6457 times the divided by the derivative evaluated at 2.6457. And so you do that calculation, and we get 2.64575. So with 3 iterations, I'm able to approximate the square root of 7 to 5 decimal places using Newton's method. Now, the way this works is kind of like this. I'll try to show you here. Here's the number I chose first. Okay, here's the number I chose first. Now, when I evaluated the function at 2.5, this just shows you what I got. So that shows you that I'm negative 0.75 units off. Okay, but then you draw the tangent line to the function. So if you draw the tangent line to the function, it hits the x-axis at this new value, 2.65. Okay, and then in the next iteration, there's 2.65. See, it's actually much closer to the answer, see, because that's 0.0225. So that's much closer to the answer, to the correct answer. But then when I draw the tangent line through that point, it hits the x-axis at 2.6457. And basically, the calculator, the grapher I used, told me that basically it's right on the answer. So it's not the exact answer, but it's pretty close. So 2.6457. Now, I won't do the third one, but basically that's geometrically what's happening with this particular method. Okay, let's do one more. So the function here is x cubed minus 5x plus 2, and we want to find the root that's on the interval from 0 to 1. Now, because this function might have more than one root, so we've got to be specific about where we want the root at. So now, first of all, let's check and make sure that the sign changes. If I evaluate the function at 0, then I get 2, and if I evaluate the function at 1, I get minus 2. So by the intermediate value theorem, there must be a root in 0 to 1. So I'm going to start with 0.5. Start with the number halfway between there, 0.5. Now I need the derivative. I've already got the function, so I need the derivative. The derivative is right there, 3x squared minus 5. Now, so x1, remember, is 0.5. So what's x2? x2 would be 0.5 minus the function evaluated at 0.5, so plug that in there, and then divided by the derivative evaluated at 0.5, so plug that in there. And you can see here I tried to show you, how I plugged it into the function and plugged it into the derivative. And then I got 0.4118. Okay, now, so to get the third iteration, or get the third point, then you take x2, which is 0.4118, minus the function evaluated at that number, divided by the derivative evaluated at that number, and then you do that calculation, you get 0.4142. And then if you want to get another one, for x4, you would take 0.4142 minus the function evaluated at that number, divided by the derivative evaluated at that number, and notice it gave me the same thing. So the second iteration and the third iteration, I got back the same answer to 4 decimal places. So the answer accurate to 4 decimal places is just 0.4142. Now you can check the answer to see how close to 0 you get. So when you plug it back in here, 0.4142 cubed minus 5 times 0.4142 plus 2 gave me 0.000061. And obviously, if you needed more accuracy, you could take this out to more decimal places. All right. So it's good that I showed you this one, because this is one, the one I showed you before that, we knew the answer was going to be square root of 7, and so we could just cheat it and got the answer. But on this one, we were not necessarily going to know what the answer is. So on this one, we have to do it with those iterations. Now, I want to end this discussion to show you that Newton's method doesn't always work. So what if I wanted to use Newton's method to estimate a 0 for the function cube root of x? Okay, well, we know the 0 is x equals 0. And we know it's in the interval from negative 0.2 to 0.2. So what happens if you try a number like 0.1? Okay, now you can show that the derivative of this is just 1 over 3 x to the 2/3. Now let's take a look at what happens. So if we tried this at 0.1, our first iteration would be 0.1 minus the function evaluated at 0.1 divided by the derivative evaluated at 0.1, and then that gave me negative 0.2. Now let's try to use negative 0.2 and find x3. So now evaluate, you get negative 0.2 minus the function evaluated at negative 0.2 divided by the derivative evaluated at negative 0.2, and I get 0.04. And let's do it again. At 0.04, I would have 0.04 minus the function evaluated at 0.04 divided by the derivative evaluated at 0.04, which gives me negative 0.8. So since we know what the answer, we know the answer should be 0. Look what's happening here. We keep getting farther and farther away from 0. I know we get a negative, then a positive, then negative, but still we're getting farther and farther away from 0. So what's happening here? Well, remember the first thing here's my function. Here's the function of cube root of x, this red one. And now at point 1, I'm actually 0.464 away from it, okay? But now what happens if I draw the tangent line? See what happens when I draw the tangent line? It shoots it way out here. So instead of shooting it somewhere down here real close to the function, it's shooting it way out there where it should have shot it down here close to 0 if this was going to work. But it shot it farther away. And then if you try that one, well, here's negative 0.2. And now look what happens when you draw the tangent line to this graph at negative 0.2. Now look at the tangent line. It goes way out here. So it's even getting farther and farther away. And then that would correspond with the point up here. And then when you draw the tangent line for that point, you're going to be way over here somewhere. And actually you're going to be at negative 0.8. So this doesn't always work. So just make sure that when you're working these problems, it works pretty well on polynomials, but on some of these functions that have radicals and maybe rational functions and things like that, it doesn't work too well. So anyway, I wanted to make sure I showed you Newton's method because that is an application of derivatives. And so that completes my calculus conundrums on applications of derivatives. And so I'll start my next conundrums on evaluating integrals at some point.